Well, thank you so much for coming back to the third talk of this session. And we will have Everett Howe speaking on determining whether an isogeny class contains a Jacobian Part II prospects and questions.
Yes, thank you, Rachel, and thank you again to the organizers. I wasn't entirely certain how this two-part talk structure would work out in practice. So what I have done is I have come up with a variety of questions that we might be able to consider, at least some of which might possibly be approachable, and some of which I think probably aren't, but you never know. That might shed light on the problem that I talked about in part one of this talk, determining whether or not there is a Jacobian in an isogeny class. But even though it's not directly maybe applicable to the problem of finding Jacobians in an isogeny class, I did also include a question about finding large, easy to analyze families of curves that can help produce examples of various sorts. So for example, if you're looking for curves with many points, it's nice to have some families that are smaller than the entire moduli space of curves, where you might have some control over the isogeny class, and you might have some ability to find examples of a sort you're looking for. So the final question is about that. So first, at my talk yesterday, Nils asked, is there any intuition on whether there is a finite set of methods or criteria that can give necessary and sufficient conditions? And I couldn't remember whether this was a question about principally polarized varieties in isogeny classes or Jacobians in isogeny classes. So I'm going to take it both ways. With principally polarized varieties in isogeny classes, my intuition would be that yes, there is some kind of chance, and the only evidence I have is that the problem is completely answered for ordinary isogeny classes. If somebody gives you an ordinary isogeny class, there is a procedure you can go through that will determine whether or not there is a principally polarized variety in it. And more recently, as was mentioned yesterday, there's also techniques for answering the question for some non-ordinary isogeny classes. But if the question is about Jacobians, then personally, I'm very doubtful that there's going to be any kind of straightforward method for finding out if there's a Jacobian in an isogeny class. But again, you never know. So this is the first question, which I think might be approachable. So, if there is some simple test for Jacobians in an isogeny class, then let's find like the easiest possible case of it and see if we can answer that. So here is a challenge problem. So pick some Q and let's make it at least 127 so that some simple enumerations aren't going to help you. So for some prime power at least 127, find an absolutely irreducible, ordinary, four-dimensional isogeny class over FQ, whose Weil polynomial has the property that the number field that it defines contains no roots of unity other than plus or minus 1, and the number field is ramified over its maximal real subfield. And once you have such an F, determine whether or not the isogeny class contains a Jacobian. So these conditions, I want ordinary because I'm trying to make things easier. I want absolutely irreducible because I want things to be harder. In my talk yesterday, I showed how when you're looking at non-irreducible isogeny classes, then there are techniques that you can use that help you answer this question. So let's take away those easy techniques.
There's one question in the chat. I don't know if you just answered it, but the
Oh,
computing.
we'll explore that in just a moment. So that's why absolutely irreducible. That's why ordinary. Asking that the number field contain no roots of unity is because if it does contain a root of unity, then that gives the possibility that there might be an automorphism of a curve that will provide you with a map to some smaller, I guess probably a map to P1 in this case. So let's take that out of the equation. And the number field being ramified over its maximal real subfield, that is there because that is enough to imply that there's a principally polarized variety in the isogeny class. So you have an isogeny class, there are principally polarized varieties in it. Are there any Jacobians? And as Nils has foreseen, there might be ways of cheating. And, you know, I like to say no cheating, except that cheating sometimes mean seeing a clever way around the problem. And sometimes seeing a clever way around the problem means that you've transcended the predictions of how the problem should be solved, and you've found another way. So, you know, if you can find another way, please go ahead and be clever. But there are some ways that I think would be missing the spirit of the challenge. So the first idea that is just a little bit too clever, Nils, is that if you choose a genus 4 curve over FQ and compute its Vey polynomial, and repeat that until your F satisfies the requirements on the preceding page, and choose that for your F, then you can say there's a Jacobian in there. That seems like it might be missing the point. A slightly more interesting way of cheating. Suppose you choose a genus 4 curve, and let's say that its automorphism group is trivial, and you compute its Vey polynomial, and you repeat this until you find a Vey polynomial f naught, which suggests we're going to be changing something. Repeat until your f naught satisfies the requirements, and there's only one principally polarized abelian variety in the isogeny class. You can check that, and you might have to wait a while before, if you're choosing your curve randomly, you might have to wait a while before this happens, but maybe you'll wait less time than the q to the 9th that you would need to wait to enumerate curves. But once you find such an f naught, you take your f for the challenge to be f naught of negative x. So that corresponds to the quadratic twist of the Jacobian that you just found. And if there's only one principally polarized abelian variety, and it's the twist of a Jacobian that has no automorphisms, then that principally polarized abelian variety is not a Jacobian. So this is a way that you might be able to find an example where your isogeny class does not contain a Jacobian, but I think it's still cheating.
Everett, there's some questions in the chat. Do you want to take them at the end or during the talk?
I can look at this. Any chance that one could determine the possibilities for the singularity of the theta divisor at 0, and then use the solution to the Schottky problem in dimension 4? And Arman asks the same question, essentially. I suppose there is a chance. I don't know how computationally friendly this is, but there you go. That might be a way of solving this problem, which would be really interesting to do. But if you're having trouble convincing your friends that you didn't cheat, then here is an example that you can take. Here is a real Vey polynomial for, oops, here's the problem with drawing with your mouse. Your coffee cup gets in the way. So there's a real Vey polynomial over the field with 127 elements. It has the nice property that the ring generated by Frobenius and Verschiebung is the maximal order, which can only help you, I think. And I promise, honest, that I chose it by picking coefficients at random from a reasonable region inside the parameter space of Vey polynomials. So the challenge question is there a Jacobian with that real Vey polynomial? I would be interested if someone could answer that. So here is another challenge, which would be related to the other interpretation of Nill's question. So consider one of the equivalences of categories that is not Deline's. So there is the Centelleje sticks category equivalence for abelian varieties over Fp with no real Frobenius eigenvalues. And there's the Oswald-Shankar equivalence that involves almost ordinary abelian varieties over Fq. So there are things, those are two things that are analogous to Deline's equivalence. So can you find an efficient procedure to decide whether an isogeny class that's covered by one of these category equivalences, can you find an efficient procedure to decide whether an isogeny class of such varieties contains a principally polarized abelian variety? And you have to be aware that there is work on this. Bergstrom and Karamacher and Marcellia have a paper out where they have shown how to do this for many isogeny classes, but if I understand correctly, not all of them. There are exceptions where things don't work out. So the challenge would be to come up with something that includes more isogeny classes. Okay. Or if you want a real challenge, come up with a new equivalence of categories from some collection of non-ordinary abelian varieties to some category of, say, modules with extra structure that you can compute more easily with. And as I joked yesterday, 30 years ago when I was in Michigan, Milne said that maybe you could do this using representations of gerbes. So if you find that hint helpful, go ahead and use it. I personally did not. But that is just the limitations of my mathematical education. So maybe I should pause for a moment here because I was going to move on from the topic that I talked about yesterday to looking at large families of easy to compute curves. So I can pause if there are any other questions that people have. This would be a good time to ask. There's discussion happening in the chat, but I think it's discussion and not questions. I think people are busy working on solving the problem for genus 4 curves, so that is good. So let me move then to the problem of finding easy to compute families, and maybe to give you more of a hint of what I'm thinking about, I'll look at the case of genus 4 curves. So when you're searching for examples of curves with many points or with other properties, it's nice to have some families that are easy to control. And something that has worked well for me in a couple of situations is genus 4 curves that come with an action of the Klein 4 group. So there are three possibilities. If you have a genus 4 curve and a Klein 4 group in its automorphism group, there are three possibilities. Maybe your Klein 4 group contains a hyperelliptic involution, or maybe it does not. And in that case, there are two possibilities. Either when you mod out by the full V4 subgroup, you get a projective line. I'm thinking, yeah, I'm working over a finite field. Or when you mod out by the V4 subgroup, you get a curve of genus 1. So let's look at those possibilities. So if your V4 contains a hyperelliptic involution, then you get a diagram like this. So each of these maps is a double cover. One of, here is the hyperelliptic involution, and here are the other two involutions. In this arrangement, two of the intermediate covers have genus 2, these two curves, and the third is again a P1. And the Jacobian of that should not be an X, that should be a D, decomposes as, oops, never mind, decomposes as the product of the Jacobians of the two C's. And to construct something like this, you need to have the ramification points of this cover of P1 and this cover of P1. They need to line up correctly. So here's my little schematic diagram. There are 6 points in P1 that ramify going up to C1, and there are 6 that ramify going up to C2. And in order for this middle curve to have genus 0, when you add these together mod 2, you need to have 2 ramification points. So this is the alignment that you have to have. And one way of thinking about this is that you can start with your favorite curve C1. So that gives you these 6 ramification points. And then you get a discrete invariant. You get to choose which of those 6 you're going to throw away. And then you get a continuous parameter. You get to choose what new point of P1 are you going to throw in as the new ramification point. And then you'll get a diagram like this. And one issue is that if you, again, start with your favorite C1 and you're hoping to get your favorite C2, it's unlikely to work because there are about Q cubed possible C2s and you only have 1 parameter to play with. So you're likely not going to be able to take your 2 favorite genus 2 curves and put them together. Or you might only be worried about isogeny classes. And then, you know, there are the big O of Q to the 3 have isogeny classes of genus 2 curves. So you have maybe a slightly better chance, 1 chance out of square root of Q, of being able to get something in your favorite isogeny class as your second curve. So this may not be the most useful construction, but it's one of the 3, so I figured I would mention it. Here's another possibility. The V4 involutions are not hyperelliptic, and the quotient of D by the whole V4 subgroup is a P1. Again, this X should be a D. So in this case, you have an elliptic curve, another elliptic curve, and a genus 2 curve. And the Jacobian of D decomposes as up to isogeny as the product of the Jacobian of C with the 2 E's. And here, again, ramification has to line up correctly. Your E1 is ramified over P1 at 4 ramification points. The E2 is also ramified at 4. And to get a genus 2 curve in the middle, when you add these points up modulo 2, you need to end up with 6 points. And here, there's an interesting way of producing examples. It's tempting to start with an elliptic curve and another elliptic curve and see what happens, but it turns out in some applications it was easier to start with your curve C, and then you have a discrete invariant, which is choosing a subset of 3 of those ramification points. And then you have a continuous parameter, which is what this point is going to be on P1. So if you start with your favorite C, you have a parameter to play with, you have Q squared possibilities for the E1 and E2, so you've got 1 chance out of Q that you can get your favorite elliptic curves here. If you only care about the isogeny classes, well, there are about order of Q possible pairs of isogeny classes for the E's, and you have a parameter. So you have a fair chance of getting your favorite isogeny classes of E's represented by these 2 curves on the outside. And the final possibility is your involutions are non-hyperelliptic, and when you quotient out D by all of the V4, you get a genus 1 curve at the bottom. And if you work out the numerology, the only way this can happen is if all of the intermediate curves have genus 2. If you have a genus 2 curve with a map to an elliptic curve, then its Jacobian is isogynous to E times another elliptic curve. So we're going to say that Jac CI is isogynous to E times EI for some elliptic curve EI. And then the Jacobian of D decomposes again as the product of E with E1, E2, and E3. And you still have some ramification restrictions. If C over E1 ramifies at 2 points, and a genus 2 double cover of a genus 1 curve in characteristic not 2 has to have these 2 ramification points. C2 also needs 2 ramification points, and C3 also needs 2 ramification points. And so for everything to fit in this diagram, the ramification points have to line up in this manner. And here you have some more freedom. You can pick your E and your E1 and your E2 pretty much however you want, and you have no parameters left to play with, but then you just get one elliptic curve left over. So the trade-off here is that you get more freedom in what you can demand of the construction, and then you have to hope for your last elliptic curve to do whatever it is you want it to do. So, as I said, these things can be useful. The first, it doesn't have a whole lot of flexibility, so I'm not going to look at it too much. The second construction, there's a little more freedom. I used this in a paper in 2016 to quickly construct genus 4 curves with small defect. And the idea was to start with a C that had small defect. Let this other ramification point vary. Actually, you don't even need to make it vary. You can figure out what it has to be in order to get an E1 that you like. So it's a computation. You choose an E1 with small defect, you figure out what this ramification point has to be, and you check whether this E2 also has small defect. So it's very fast. And I was able to get, for actual numerical values of Q, various small defect genus 4 curves. And heuristically, there's an argument that shows that for large enough Q, you should probably be able to get defect less than or equal to 4. In practice, for all the primes less than a million or something like that, 96.5% of the time I got defect less than 4. And the exceptions were getting more rare. Another application from last year was that Kudo and Harashita and I managed to quickly construct super special curves for various characteristics. I don't remember how far up we went, but it was certainly in the tens of thousands. So. And the third construction also has a lot of freedom, and it always gives you completely split Jacobians. And it has an interesting property that if you're working over the algebraic closure, if you take the bottom curve to have j equals 0, it turns out you can take the other 3 elliptic curves to be the same elliptic curve that can be anything you want, and you can fit it together in the diagram. And I could say more about that if there's a little bit more time at the end. So the challenge is to find similar constructions for larger genus. That is, constructions that let us quickly build up genus G curves from lower genus curves with as much freedom as possible. So the web page suggested that there be about 30 minutes of this plus time for questions. I'm a little bit short. I could say a little bit more about that third construction, or if people have questions or comments, we can also address them now.
Does anyone have any questions?
Hey, this is Jeff.
Hi.
Hi. That was a lot of fun. One other way that one could push this, if one wanted to, is there's a not quite a tension, but so there's a conjecture by Shankar and Zimmerman which says that over FP bar, anything should be in genus 4 or A4, anything should be isogynous to a Jacobian. And so in cases when an isogeny class doesn't yet contain a Jacobian, it might be interesting, or might not be for that matter, to know when it does start containing a Jacobian as predicted. Like, sorry, where when means like as you increase the size of the base field. Sorry, so you start off over FP and there are no Jacobians yet, but the isogeny class gets bigger, and conjecturally it will eventually contain a Jacobian if you're willing to admit a big power of P.
Yeah, that would definitely be interesting. Though I think for genera this small, you also would expect the isogeny class to already contain one, because there are not that many isogeny classes compared to the number of curves you have.
Mm-hmm.
But sure, as you increase the base field, you would certainly expect to find.
Yeah, and the Shankar-Zimmerman conjecture is basically by just crude estimates of size of isogeny classes versus numbers of points in them, that kind of thing. So it's not.
Yeah.
Nothing's incompatible.
Good, thank you. And Christoph, yeah.
Yeah, I just wanted to comment a bit more on your first challenge.
Yes.
Because somehow, I mean, yeah, indeed, you took the worst case in the following sense that, I mean, you would have given something which is not absolutely irreducible. Then what we did in the paper with Marcus and Kirschmer, Narbonne, and Robert, we could have done the computation of the Schottky form over the ground field exactly. So we could have really checked, I mean, if you fall inside the Jacobian locus. Still, I mean, that would not have been a complete solution, because then you still have to solve the Serre's obstruction problem. And for genus 4, I have no idea how, I mean, even to express exactly necessary and sufficient condition to be a Jacobian over the ground field. I mean, this is a completely open question for genus 4. And then, I mean, taking an absolutely irreducible, that's the problem. I mean, it's a bit like, I don't know how to do exact computation of this kind of thing. I mean, all you can do is lift over C. Then, I mean, as it was suggested by Bjorn and Niels, you could go to lattices. Then you could like do an approximate computation of thetas. So you could like, if you normalize them correctly, you could find something that would be some algebraic number, and then recognize if you are, I mean, if you are 0 or not to be in the Schottky locus. I mean, so that's easy, but it would still be very heuristic. And then also the problem is, you could say, at least if you would have a procedure to reconstruct a curve in genus 4, I mean, if you know that, I mean, your abelian variety is a Jacobian, if you have a procedure to reconstruct from the thetas the Jacobian, or sorry, the curve, then, I mean, you could reduce it, check that everything is fine, and compute the number of points and see if you are not indeed inside the isogeny class. But for genus 4, I don't think that anybody has done this either. I mean, to be able to reconstruct the curve from the Jacobian. Yeah. So, I mean, indeed, I mean, you really chose very carefully your problem. And, that would be probably very, very hard.
I think so as well, but you know, there are still these little hints that maybe there are avenues of approaching it. So
did you choose at least the discriminant of your real?
Oh, I did. I looked to see what it was. I did not condition anything on it. And under GRH, the class group of the field was pretty darn big, and the class group of the real subfield was order 4 or order 2 or something like that. So there are lots of abelian varieties in the isogeny class.
Thanks.
Let's see, David, do you have a question?
Yeah. So my question was, you chose the Klein 4 group as your automorphism group in this example for genus 4.
Yes.
In higher genus, kind of what, do you have ideas for what kind of amenable automorphism groups would be to look for?
You know, I think anything that makes it easy for you. So still having a Klein 4 group could definitely be something that works out. I haven't worked out all the details, but you can draw those little diagrams and break up your genus 5 curve into, you know, 2 elliptic curves and a genus 3. But then genus 3 curves are kind of hard to control. So maybe you'd rather have 2 genus 2s and an elliptic curve, you know, so there's lots of variation. But you know, if you wanted to have a larger automorphism group, if you wanted to have a group of order 8, you know, C2 times C2 times C2 or something, that's also kind of easy to understand. And your Jacobian breaks down into smaller pieces, but then it's, you know, harder to piece them together. So there's all kinds of trade-offs which are not always easy to articulate.
One of the troubles when you get to higher an elementary abelian group of like Z mod 2 to the R is that the relationships between the branch loci get more and more constrained.
Yeah, definitely. But it also depends on your application. So when I had been thinking about this, I was mostly thinking about trying to find curves with many points. So I really wanted to, you know, look at odd corners of the moduli space where there aren't very many curves and try to piece them together somehow.
Well, Everett, we have lots of time, so if there's something else you'd like to talk about, you know, feel free to go ahead. Or
yeah, I wasn't sure how many questions there would be, so I have the last page of my slides, but secretly there's page 17 of 16. Oh, with a typo. Go away. So let's review this third construction over the algebraic closure this time, so I don't have to worry about rationality of anything. And this is, I stole some of these slides from a talk I gave last fall, but this is not something I have used anywhere or talked about much. So I'm also trying to advertise this because I think there's something really interesting here. So let's look at this third construction, but now over the algebraic closure. So again, you have a curve D, you have a V4 group acting on it, and the bottom curve is an elliptic curve. So each of these genus 2 curves is not just isogynous to E times EI, you can choose it so it's 2 power isogynous to E times EI. And again, the Jacobian of the top curve decomposes as the product of all of these E's, and the ramification points have to line up. So let's analyze this a little bit more. What does a genus 2 double cover of an elliptic curve look like? So suppose our elliptic curve at the bottom of the diagram is given in this form. Every genus 2 double cover of E can be written as Z squared equals F, where the divisor of F has 2 points with multiplicity 1, and then you have to subtract an S. And in order for this to work, this condition has to hold in the group of points of E. If you translate everything by minus S, you get an isomorphic cover where now the divisor of F is a point, and the point's opposite minus twice their minus twice the origin. So the interesting thing is that the orbit of this point P under the automorphism group of E is an invariant of the cover. So when the automorphism group is plus or minus 1, what that means is that the x coordinate of this point P is an invariant of the cover. So let's see what happens when we glue some elliptic curves together. Suppose someone gives you another elliptic curve F that's given in this form with a mu now for its lambda invariant. And suppose you look at the isomorphism of these two groups, the two torsion of E and the two torsion of F, that sends 0, 0 to 0, 0, 1, 0 to 1, 0, and lambda 0 to mu 0. If you take the quotient of this abelian surface, E times F, by the graph of this isomorphism, you get a surface that has a principal polarization. So it's usually a genus 2 curve. The condition is that lambda be different from mu. And so you'll get a genus 2 curve with a degree 2 map. And you could look at the invariant that I just described on the previous page and figure out what that invariant is for this double cover. And it is this. There's a formula for it, and it's not even that bad. So what does this have to do with the construction? So given 3 covers of E by genus 2 curves, you can ask, when can we line the ramifications up point, the ramification points up in order to get a genus 4 curve, as in the diagram. And we can express this answer in terms of the invariants, xi, or of the points pi, which are determined only up to sign. So remember, the pi were the points where your double cover of E was ramified, normalized so that the 2 ramification points were opposite of one another. The pi are only determined up to sign, but there is going to be an answer that you can express in terms of these points or these x's. And the answer is that the 3 covers can be lined up correctly if and only if we can choose signs so that this, plus or minus P1, plus or minus P2, plus or minus P3 is 0 on E. And the other way you can express that is that you can line the 3 covers up correctly if the third summation polynomial for E, evaluated on x1, x2, x3, is 0. So that's a very explicit relationship. We have formulas for the xi in terms of the lambdas and the mu's. We know what the third summation polynomial looks like for an elliptic curve. And you piece all those things together and you find out that the 3 covers can be lined up correctly if and only if the lambda invariant for E satisfies this relation with the symmetric functions in the mu's. So it's a polynomial relation, which is just, I think, amazing. And as an application, let's look at finding super special curves. So we're going to be working in characteristic P. Let's work over the algebraic closure. For prime P, you can list all the supersingular lambda invariants. And there are P minus 1 over 2 of them. And they're elements of Fp squared. And then you could enumerate all of the quadruples of lambda invariants of 4 elliptic curves. The lambda has to be different from the mu i's in order to glue things together. But then we can plug these values into the polynomial on the preceding page and see whether the value is 0. So we have about p to the 4th possible combinations of lambdas and mu's. When you evaluate the polynomial, we'll get an element of Fp squared. If everything is going right with the universe, there should be a probability of 1 over p squared, that value is 0. So you expect that there are going to be p squared quadruples that will work. And in actual practice, when you do some calculations, that's what you see. You see that for a given p, you find lots of quadruples of lambda invariants of elliptic curves, of supersingular elliptic curves that meet, that satisfy this polynomial. So for every prime bigger than 13 that I've tried, I found examples. So that gives you a quick way for p bigger than 13 to find a superspecial genus 4 curve. And the tempting thought is that you've got a simple polynomial. And surely someone should be able to prove that you have enough supersingular lambda invariants that you can plug them into this polynomial and get 0. You would hope. I haven't been able to do that. I also haven't tried that hard yet. So, you know, I encourage other people to look at it, because it would be really neat to have a proof that there are super special genus 4 curves in every characteristic. And the last thing I will mention, suppose someone gives you an elliptic curve f given by this Legendre form. And suppose we take our mu1, mu2, and mu3 to be 3 of the different transformations of mu that give you the same elliptic curve. So we take mu1, mu2, mu3 to be those things. And then you plug those values into the polynomial from the corollary a couple pages back. And that polynomial, which was not that complicated to begin with, it becomes much simpler. It turns into this. It doesn't depend on mu at all. And the lambda values you get correspond to the j equals 0 curve. So what that means is that if you let E be the elliptic curve with j invariant 0, and you let F be any other elliptic curve, then you can explicitly construct a genus 4 curve whose Jacobian is 2 power isogynous to E times F cubed. So that's also kind of a beautiful thing, I think. So in particular, if the genus 0 curve has some property that you like maybe it has many points, or maybe it's supersingular, or whatever, then you can choose another curve that also has some property you like, and you have a genus 4 curve whose Jacobian splits up into those curves. So that is the end of the bonus slides, which also takes me close to the end of the talk, so I can honestly go to the thanks at the end. So again, thanks to Sarah for creating the course, creating the notes, helping everyone by getting this book published. Thank you to the organizer of the conference for managing to make this all work in a pandemic. Thank you for listening. Thanks to everyone who has contributed to the beautiful results in the field, and to those who will contribute in the future.
Well, thank you, Everett. Let's all give Everett a round of applause. Well, I guess there's time for a few more questions. Maybe I'll start with one. So in that last slide, could you also construct something with a number 3?
With a number 3, so that would be
by taking F to be like a supersingular elliptic curve, and
yes,
then,
yeah.
Oh no, but only for some characteristics, I guess, because you have the J invariant 0. So,
but you only want a number 3, so
you need that one to be ordinary. So that will.
Oh, right. Yes, right.
Yeah.
But on the other hand, you know, given the more general condition, you can choose your mu's. Well, you could choose your mu's to be supersingular and then solve for lambda, and then hope that it's not supersingular. And then there must be some way of ensuring that will happen, you would hope.
Yeah.
Bjorn?
Oh yeah, thank you for these talks. So I really like that last corollary you put on the at the very end. I'm just wondering if this may be unrelated. I was just wondering if it's connected at all to these constructions of Bogomolf and Chinkel, where these are the ones where they start with some curve and they find that it has, like for example, every genus 2 curve has an unramified cover that maps down to a particular genus 2 curve. And so that particular genus 2 curve is like x is y squared equals x to the 6th minus 1. And so it has this same e in it. And so it's just another family of curves where you have sort of a moving family of curves, but it's all dominating this particular thing. I don't know. It just looked like there might be some connection between this family and some of the families that they have in there.
There could. I don't think I know of this particular work. So
yeah, maybe I can find. I'll try to find it and paste it in chat. I think it's called Unramified Correspondences.
And I will make a note.
Yeah.
All right, I'll look. Thank you.
Let's see,
Niels?
Neil.
Yeah. Hi, Everett. Thank you very much for the talk. My question was actually a little bit along the same lines as Bjorn's. So, because I mean, you find this corollary which looks really surprising when you arrive it along this road, but it's telling you something about how the Schottky locus is intersecting with some other special strata, right?
Yes.
So
yeah.
I'm wondering, sort of in hindsight, now that you know that this is true, can you sort of anticipate this post factum? Sort of explain, oh yeah, no, yes, we would have been able to see this had we only looked at some general intersection theory about strata in morphology.
Oh yes, the youngest child could have predicted that. I don't know. That's an interesting thought. Like taking abelian varieties that are, you know, a small isogeny away from a product of elliptic curves and looking to see, yeah, I don't know.
Yeah, but perhaps I could invite one of the hosts, Rachel, to comment on that. She might have an idea.
I don't know. Darren Glass and I, a long time ago, this is not really answering your question directly, but we looked at these fiber products of elliptic curves and sort of saw similar, sort of being able to produce things with large A number in that sense. I was also, I wasn't totally paying attention because I was looking up these results of Montanucci, who I think is speaking this week also, and genera of quotients of the Fermat of the Hermitian curve, and wondering when the genus 4 is a genera of a quotient of the Hermitian curve.
Look forward to hearing about that.
Everett, I had a question.
Yes, hi.
Suppose you have some amazing curve whose Jacobian is isogynous to the product of n copies of a given elliptic curve. I'm thinking actually of the Fricka-McBeath curve, for example.
Yeah.
And suppose you also know what the Mordell-Weil lattice is, namely how many morphisms there are from the curve to this elliptic curve of every degree. Does that allow you to reconstruct the Jacobian, or even better, the curve from the elliptic curve and the lattice?
That's an interesting question.
I mean, I know you can build these abelian varieties from unimodular positive definite lattices and elliptic curves, but then it's isomorphic to n copies of the elliptic curve. But the Fricka-McBeath curve isn't isomorphic to 7 copies of an elliptic curve, just isogynous. But if you knew the Mordell-Weil lattice, could you get back the Jacobian?
Would you give yourself the polarization as well?
Yeah, I mean, I give myself the Mordell-Weil lattice as a Euclidean lattice, namely how many morphisms there are of each degree to this fixed elliptic curve.
Right. Right. So this would be morphisms from the curve itself.
Exactly,
So
exactly.
that would include the polarization information.
If you translated it to the Jacobian, it would include the polarization of the Jacobian. Yeah.
So that's right. So there's going to be questions about the genus of the Hermitian forms.
Okay. Okay.
Uh,
Yeah, I mean, in the case of Fricka McBeath, the Euclidean form is unique in its genus. You know, everything is nice.
Everything is nice.
It basically
Okay.
comes from the E7 weight lattice. And I just wondered if you can go, if it would be an independent construction of the curve, just starting from this one elliptic curve and that lattice.
For that case, maybe that would be an interesting
Test
way
case
of
of
reaching
this.
it. Yeah.
Yeah. Okay. Back to mute.
Yeah. Thank you.
I don't see any other. Oh no, one more hand up.
Christoph. Yeah.
Yeah.
Yeah. If you, I mean, your equation in terms of mu and lambda. Oh, yeah. Well, and this one. So, okay. So how many variables do you have at the end? You have like four.
Yes.
Four variables.
Though someone noticed in a previous talk that there's some expression which seems to appear all the time.
Yeah, because I was wondering, I mean.
Yeah, S1 minus S2.
Yeah.
You could call it in a different way.
Yes, because there it's squared and there it's linear and there it's yes.
No, I mean, just to know, I mean, as this, like, I mean, then it would be what?
Plain pocket.
No, I mean, there are more variables.
Yeah, so, but you can keep the S1 and S2. The S2 minus S1, you can call it like another variable. So in fact, this another variable, lambda and x3. So it is a plane quartet. But I don't know if it is similar.
So you would look at it as a cover of a plane quartet, I mean, somehow, because then, I mean, your symmetric functions, you have to redecompose them. No, I mean, just to try, I mean, to see if you could say something on this geometric object, like number of points it would have or something, and then see, I mean, then you need to look very special points because you want like to impose them to come from values from super singular curves, right?
Yeah.
And also maybe a question which is not directly related to this, but I mean, maybe that's the question one should ask, like the typical question now. So what do you think is going to be the general situation when the genus grow? Because the interview says that it doesn't dare to conjecture if there is a maximal curve at the distance which is bounded for the Hasse-Servel bound. I mean, so any opinion? Or?
Oh, heavens.
Genus 4, now you find 4, so I mean, that's great.
Yes. So, yeah, once you get for the, so the small genera, even when they start getting to be, you know, higher up in the single digits, they still feel kind of like friendly people who you can like get to know. And when you get to the double digits or worse, then it feels like, oh, what is going on? So for the smaller ones, it still seems like there might be hope of coming up with weird constructions like this that look at special cases, and you can still like get lots of points. And so that's the way I have been cheating my whole life in this area, was by looking at these kind of exceptional things and not worrying too much about the higher genera. So when you get up to the higher genera, I really am not sure what happens.
Okay. So the threshold would be about saying that the moduli space becomes of general type or something like this, and then you would say that everything is lost.
My understanding is lost. How about that? And what the truth of the numbers is, I don't know.
Thanks.
So the related question you could ask along those lines is, let's say you want to find a smooth curve and look at its Newton polygon and say that it has only slopes 0, 1, and a half, then what's sort of the largest amount of you want to hit every genus, but get the number of slopes 1/2 to be as large as possible relative to the genus. And so recently with Wan Lin and Elena and Yan Cheng, we sort of found a sort of a construction of a family of Z-mod 3 covers that would hit a very high proportion of slopes of 1/2. Well, this has been a really fun discussion. Thank you, Everett, for just a talk that generated so many interesting questions and comments. I think now there's an hour. Let's thank Everett again. All right, so I think now there's an hour break, and then we'll come back with a different host in an hour.
Thanks a lot, Rachel.
Have a good break.
Everett, I sent you on the mail a link.
Okay. I will get there. Okay, good. And see everyone in an hour.